When acceleration changes with time, the standard kinematic equations break down. A car's brakes ramp up gradually. A rocket's thrust shifts as fuel burns. To handle these situations, we need integration. This video walks through two complete problems: a polynomial acceleration integrated twice to find velocity and position, then a piecewise braking scenario where a bicycle catches a decelerating car. Consider an acceleration that varies as a polynomial in time. The acceleration a of t equals b0 plus b1 times t plus b2 times t squared. On the acceleration versus time graph, the curve starts at b0 on the vertical axis and curves upward, with initial slope b1. This general form captures a constant baseline, a linear ramp, and quadratic curvature. Let v0 be the initial velocity at t equals 0. We integrate this expression to find velocity, then integrate again to find position. The change in velocity equals the integral of acceleration over time. So v of t minus v0 equals the integral from 0 to t of a of t prime dt prime. Now substitute the polynomial for acceleration. This becomes the integral from 0 to t of b0 plus b1 times t prime plus b2 times t prime squared dt prime. We integrate each term separately. b0 being a constant integrates to b0 times t. b1 times t prime integrates to b1 times t squared over 2. Notice the exponent increases by 1, and we divide by that new exponent. b2 times t prime squared integrates to b2 times t cubed over 3 by the same power rule. Combining everything and adding back v0, we get v of t equals v0 plus b0 times t plus b1 times t squared over 2 plus b2 times t cubed over 3. Each coefficient from the acceleration produces a velocity term 1 degree higher. Now integrate velocity to obtain position. Let x0 be the initial position. Then x of t minus x0 equals the integral from 0 to t of v of t prime dt prime. Substitute the velocity expression and integrate term by term. The constant v0 integrates to v0 times t. The term b0 times t prime gives b0 t squared over 2. The term b1 over 2 times t prime squared gives b1 t cubed over 6, since the denominator is 2 times 3. And b2 over 3 times t prime cubed gives b2t to the 4th over 12, since 3 times 4 is 12. So the complete position function is x of t equals x0 plus v0 t plus b0 over 2t squared plus b1 over 6t cubed plus b2 over 12t to the 4th. Two successive integrations turn a quadratic acceleration into a quartic position. Compare the three functions side by side. Acceleration has terms up to t squared, degree 2. Velocity reaches t cubed, degree 3. Position reaches t to the 4th, degree 4. Each coefficient migrates through the chain, gaining 1 power of t and an accumulating denominator at each step. Look at the coefficient b2. In acceleration, its denominator is 1. In velocity, it becomes 1/3, and in position, it becomes 1/12. So the chain runs 1, 3, 12. Likewise, for b1, the denominator chain runs 1, 2, 6. This pattern holds for any polynomial acceleration. This term-by-term approach works when acceleration is a single polynomial over the entire time interval. But real scenarios often involve acceleration that changes form. 0 during coasting, then a ramp during braking. For piecewise acceleration, split the timeline at each transition point and integrate each interval separately. Velocity and position must be continuous at every boundary. The final state of one interval becomes the initial condition for the next. Forgetting to carry forward these boundary values is the most common error in piecewise problems. Worked example 4.6, the bicycle and the car. A car passes through a green light at time t equals 0 at position x equals 0, traveling at 12 meters per second. At t1 equal to 1 second, the driver starts braking. The car's acceleration is piecewise. It is 0 from t equals 0 up to t1, and then it equals b times the quantity t minus t1 for t between t1, and the stopping time t2. Here b equals negative 6 meters per second cubed. This braking acceleration starts at 0 when t equals t1 and grows more negative over time, so the brakes engage gradually. The car decelerates until it stops at t2. Meanwhile, a bicycle rider moves at a constant speed, v sub b, starting 17 meters behind the car at t equals 0. The bicycle reaches the car exactly when it stops. Part A. Find velocity and position. During the first interval, from 0 to 1 second, the acceleration is 0, so the velocity stays constant at 12 meters per second. For the braking phase, we integrate starting from t1, the start of this interval, not from 0. The velocity change is v sub c of t minus v sub c of t1 equals the integral from t1 to t of b times the quantity t prime minus t1 dt prime. The antiderivative is b over 2 times the quantity t prime minus t1 squared. Check that derivative. Differentiating gives b over 2 times the quantity t prime minus t1, which is b times the quantity t prime minus t1, exactly our integrand. Now evaluate from t1 to t. The lower limit gives 0 because the squared factor vanishes there. The upper limit gives b over 2 times the quantity t minus t1 squared. Velocity is continuous at the boundary, so v sub c of t1 equals 12 meters per second. The braking velocity is therefore v sub c of t equals 12 plus b over 2 times the quantity t minus t1 squared. For position, we split the integral at t1. In the first phase, s sub c of t equals 12 times t, since the car starts at the origin, at t1 equal to 1 second. S sub c equals 12 meters. For the braking phase, we integrate the velocity from t1 to t, so x sub c of t equals x sub c of t1 plus the integral from t1 to t of the braking velocity. The constant 12 integrates to 12 times the quantity t minus t1. The quadratic term b over 2 times the quantity t prime minus t1 squared integrates to b over 6 times the quantity t minus t1 cubed. The power goes from 2 to 3, and dividing by 3 converts b over 2 into b over 6. The complete braking phase position is x sub c of t equals 12 plus 12 times the quantity t minus t1 plus b over 6 times the quantity t minus t1 cubed. Part B, stopping, means the velocity equals 0. Set v sub c of t2 to 0. 0 equals 12 plus b over 2 times the quantity t2 minus t1 squared. Rearranging the quantity t2 minus t1 squared equals negative 2 times 12 over b. Substituting b equals negative 6, we get negative 24 over negative 6, which is 4. Taking the positive square root, t2 minus t1 equals 2 seconds. So t2 equals 1 plus 2, giving 3 seconds. Now the car's position at t2. Since t2 minus t1 equals 2, we substitute x sub c of 3 equals 12 plus 12 times 2 plus b over 6 times 2 cubed. Note that b over 6 is negative 1, so we get 12 plus 24 minus 8, giving 28 meters. Now the bicycle. It starts at negative 17 meters with constant speed v sub b. Its position at time t is negative 17 plus v sub b times t. At tc equals 3 seconds, the bicycle meets the car, so set the positions equal. Negative 17 plus 3 v sub b equals 28. Then 3 v sub b equals 45, so v sub b equals 15 meters per second. 3 takeaways. Polynomial acceleration integrates term by term. Each power of t increases by 1, building higher degree velocity and position functions with factorial-like denominators. Piecewise acceleration requires integrating each interval separately, with velocity and position matched at every boundary. Position equations from different objects combine to solve meeting problems. set positions equal at the encounter time, and solve for the unknown. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.